In a video in the vectors playlist, we looked at the equation of a plane. Point A is a given point in the plane. Point P is a general point. Vector n is a vector that's perpendicular to the plane. Vector r minus a is the vector whose tail is at A and whose head is at P. Since vector r minus a is in the plane, a vector that's perpendicular to the plane, like vector n, is going to be perpendicular to this vector r minus a. That means the dot product of n with r minus a is going to be 0. To get vector r minus a, we just subtract corresponding components. So the I component is going to be x minus a1, the j component is going to be y minus a2, the k component is going to be z minus a3. The dot product of these two vectors must equal 0. To get the dot product, we multiply corresponding components. So we multiply the I components together. Then we multiply the j components. And finally we multiply the k components. So the dot product gives us a scalar, and it must work out to 0. Okay, I've gathered the x, y and z terms together, left them on the left hand side, and I've moved over the constant terms. So the components of vector n are constants. Remember, vector n is any vector that's perpendicular to the plane. It doesn't have to be a unit vector. Point A is a given point in the plane, so a1, a2 and a3 are constants. So now we see that the equation of our plane can be written in this form. Comparing, we see that A is actually n1, B is n2, C is n3. So A, B and C are the components of any vector that's perpendicular to the plane. What about the constant D? Well, if you look at this thing here, this is none other than the dot product of vector n with vector A. So we found the Cartesian equation of a plane. We could rearrange this equation to make z the subject, and we see now that z is given as a function of both x and y. So z is a function of two variables. So we could write z like this, f of xy. Let's suppose that in the general equation of a plane, b is 0 and c is 0. We get the equation ax equals d. Well, since a is some non-zero constant and d is some non-zero constant, we can write this as x equals d over a. Actually, d over a is just some constant. So the equation of the plane is x equals constant. So all the x values in the plane for any point are the same. So, for example, if we take this point here, its x value is going to be d over a. The x value of this point is also going to be d over a. So all points in the plane have the property that their x value is a constant, it's a fixed value. So this is a plane that cuts the x-axis at d over a and is parallel to the zy plane. Now suppose that both a and c are equal to 0, but b is not 0. So these terms don't appear, so we get y equals d over b. So y is a constant. So all the y values in this plane have the same value, namely the constant, which is d over b. So we're talking about a plane that cuts the y-axis at d over b and is parallel to the xz plane. Finally, we consider the case where both a and b are 0, so we don't have these terms. So we end up getting z equals d over c. So z is a constant. So all the points in the plane z equals d over c have a constant z value. So that means that all these points are at the same height above the xy plane. So we have a plane that cuts the z-axis at d over c and is parallel to the xy plane. Now d over c is shown here as a positive number. The plane is shown intersecting the positive z-axis, but of course the plane could be intersecting the negative z-axis. Similarly for these two planes are shown intersecting the positive x and y axes respectively. They could of course be intersecting the negative x and y axes. As we've seen already, we can make z the subject of the equation of a plane. So z then is seen to be a function of two variables, x and y.